Pulleys and Wedges, Type 6 Subsystems. So in 2002, we had a light, smooth pulleys connected by a light, inextensible string passing over a smooth, fixed pulley in a scale pan of weight 1 newtons. So it's not normal to get the weight given in these questions. Normally we're given the mass. So we have to be careful with that. So we have to say NB, weight given, not mass. So if we're using our F equals MA, well, we obviously need the mass, not the weight. So we have to remember that weight is equal to mass times gravity, and therefore the mass will be found by getting the weight over gravity. Okay, so just be careful about that. Okay, so again, the fact that it's a smooth pulley, no friction, smooth pulley, no friction. And again, light and extensible string, meaning we're not going to have any bouncing here, so we're not going to have any simple harmonic motion. We then have a particle of weight at 2 newtons is placed symmetrically on the centre of the scale pan. So again, everything is given in newtons. And then we have 2 particles of weight, 3n and 9n, connected by a light and extensible string, passing again over a smooth light pulley. Okay, system is released from rest. And this time, rather than looking for the acceleration of the scale pan, we're actually given the acceleration of the scale pan. And what we want to do is find the acceleration of the particle of weight 9 newtons. Okay, so let's look at the overall diagram. So I'm going to do all of my forces acting on the whole system, and then we'll break down each part into separate diagrams. We're not being asked for them here in the question, but obviously we always need to do our separate diagrams so that we can set up our equations. So if we look and start on the left hand side of the diagram, well, we have 2 separate strings, which means we're going to have 2 separate tensions. So we have tension O is acting away from the object, so acting away from the scale pan and the pulley. Then we're going to have tension acting away. So we're going to have these are pulling down on it. So we're going to have different tensions. We're going to use S for tension. And then again, tension acting away from the objects. We're going to have weight. So the weight is obviously, be careful here, well, yeah, 3 newtons and 9 newtons. So we're not going to be putting in 3G here because we're given the weight. So we're not given the mass. And same here then for this one. Well, we have a scale pan of 1 newton and a mass of 2 newtons sitting on it. So in total, the weight acting down is going to be 3. So if we're looking at that system, clearly we would say it's going to accelerate in an upward direction because the left-hand side is heavier. So this is going to accelerate down. But of course, with subsystems, what we have is a pulley system within a pulley system. So we're going to have acceleration within the system itself. So I use a different colour to represent that. So the 9 is heavier than the 3, so the 9 is going to accelerate down. So I'm going to call that acceleration B, and the 3 newton will accelerate in an upward direction. So we have to be careful with those when we're setting up our equations. Okay. So we have quite a few things going on in this system, and sometimes when we have lots of things we end up with lots of equations, but we don't necessarily need to use all of the equations. So I'm going to set up all the diagrams and set up all the equations and see which ones do we actually need to use to solve for our acceleration. So because we know what A is this time, we won't need to use all 4 equations to solve. Okay. So let's look at the first one. So we're going to start with the left and work over to the right for our force diagrams. So I'm going to start with the pulley. So with the pulley, we have the tension acting up, and we have tension acting away. Now, one thing we were told in the question was this was a smooth pulley and it's a light pulley. So if it's smooth and it's light, then if we're looking at the net forces, Well, the net forces are going to tell me that it's accelerating which way again? So yeah, sorry, it's accelerating down. So my leading force is going to be my two S's, and my opposing force is the tension upwards, and that's going to equal my mass times acceleration. But of course, the mass is 0 in this case, so therefore T is equal to 2S. So equation 1. The next one we're looking at here then is the 3 Newton. Now, 3 Newton is part of the system within the system, so we have to be careful here of our accelerations. So we have tension acting up, and we have 3 Newtons acting down, our weight. And we see that it is accelerating down and while accelerating up. So it's accelerating up while the whole system is accelerating down. So we have to be careful when you're setting up your force diagrams or your F equals ma equation for this. So whichever you're taking to be the leading acceleration, you must do the same for the other particle, so for the other 9 Newton one. Okay, so make sure you're consistent. So I'm going to take B to be my leading direction, and therefore I have to make sure B is the leading direction on the other side for the 9 Newton also. Okay, so if I'm saying B is my leading force, then that means that S minus the weight will equal the mass times the acceleration. So the tension minus the weight is 3 is equal to the mass. So as I said, up here at the top right hand corner, well, mass is weight over gravity. So the mass is going to be 3 over g times the acceleration. And of course the acceleration, so I'm taking B to be my leading direction. So then A will be in the opposite direction, so that will be B minus A. So therefore I can say that S is equal to 3 plus 3B over G minus 3A over G. So this is equation 2. I'm now going to look at the other side of the subsystem, which is the 9 Newtons. And if I look at the 9 Newton, well, my forces acting on that are S up, and weight we were given in the question is 9 Newtons. And this time when I'm looking at the accelerations, they're both actually going in the same direction. So it is going down while the system is going down. Alright, so if I set up my F equals ma, well, my leading force is clearly the weight minus the tension will equal the mass times acceleration. And again, when I set up this first line, it's always just for my head. You don't need to necessarily do this. You can go straight into subbing in your net forces. So my weight here is 9s. Mass, of course, then we said is our mass, is our weight over gravity, and our weight is 9 over g times the acceleration. Okay, so again, here we can see I've said B is the leading direction in the previous particle, the 3 Newton particle. So therefore, A is also in the same direction. So this time we're actually going to add those two accelerations, A plus B. So therefore, if I rearrange there, I can get S on its own again. And I can see that that's 9 minus 9A over G minus 9B over G. So there's equation 3. Okay, now straight away I can already see that I can get equation 2 and 3, and I can equate them. Okay, but I'm going to set up the force diagrams just for the sake of it, to show you what it would look like for the third one, which was the scale pan. Okay, so with the scale pan, we have a particle sitting on it, and therefore the weight overall for the whole thing is 3 Newtons, and we have tension acting away, and it is accelerating in an upward direction. So F equals ma. Well, my leading force is going to be my tension minus my weight equals mass times acceleration. So we have tension minus weight, which is 3 Newtons, and again our mass is our weight over gravity times the acceleration, and therefore my tension is 3 plus 3A over G. Now, of course, we have to look at the fact that we were actually told what A was, okay? So A, if we go back to the question, is G over 2. Now, you could have subbed in G over 2 at the start as well. That's perfectly fine. Or you can sub it in at this point, okay? So we're going to try and find the acceleration in terms of G of the particle 9 newtons. In other words, we're looking for the acceleration. So I'm looking for the letter B here. So I'm going to take equation 2 and equation 3, because that will only have A and B then in it, and we already know what A is, which means I can now get B on its own. But of course, you could take any kind of combination of these and probably still get the same answer out, but probably be a bit longer, okay? So I'm going to, as I said, I'm going to equate 2 and 3. And if I equate 2 and 3, well, equation 2, and go back. Equation 2 is 3 plus 3b over g. Three plus 3b over g minus 3a over g. And what does that equal? Well, that equals equation 3 there, which is 9 minus 9a over g, and that's minus 9b over g. Okay, and then we also say, but a is equal to g over 2. So we're going to now sub that in, and then we'll rearrange to get b on its own. So we have 3, let's may as well get rid of that. So we have 3b over g minus 3 over g times a, which is g over 2, is equal to, and if I bring the 3 over there, that leaves me with 6 minus 9 over g times a, which is g over 2, minus 9b over g. Okay, so if I simplify those, I have g goes into g once, and g goes into g, and then I'm left with 3b over g minus 3 over 2 is equal to 6 minus 9 over 2 minus 9b over g. So if I bring the b's to one side there, I'll have 3b over g plus 9b over g, which is 12b over g, is equal to, and then if I bring 3 over 2 over to the right hand side, I have 6 minus 9 over 2 plus 3 over 2, which equals 3, and therefore that gives me b is equal to 3g over 12, and of course we should always simplify, so we should write our answer as g over 4. So that is our acceleration of the 9 Newton particle. Okay, so what's the next part of the question? So the next part of the question says we have to find the normal reaction between the particle of the 2 Newton weight and the scale pan. So we're now going to focus in a bit more on the scale pan's diagram, but because we're looking at the reaction force of this little particle on the scale pan, we're going to have to draw a new diagram and separate out the 2 weights. Okay, so this is part 2. So we'll redraw our diagram. So we have our scale pan, and we have our particle. So when the particle is sitting on the scale pan, its weight acts on the scale pan, which we know is 2 newtons, and then the scale pan is going to react back. So we have a normal reaction, a contact force between the 2. Now we already know that it is accelerating upwards as well. So therefore, if I'm setting up my net forces equation, well, what we have is we have the leading force is going to be in the direction of motion, which is the reaction force, minus the weight is equal to mass times acceleration. So we're going to have or minus the weight is 2 is equal to the mass. And again, remember the mass isn't given in this question, it's weight. So weight is going to be mass times gravity. So therefore mass is the weight divided by gravity times A. But we know that A is equal to G over 2. And obviously 2 over G times G over 2 is 1, which gives me 1 plus 2, which is 3 newtons. So a nice little last bit added on to that. Okay, so what are our marks going for this question? So if we go back, we had our mass of our two particles. So for actually working out the mass of the two particles, in other words, for using this equation up here, we were getting 5 marks. So that's for the two particles. So if we're actually working that out. Okay, so where we had down here the 3 over G and the 9 over G, that's what you're getting your 5 marks for. Then we had 5 marks for setting up our two equations. So for setting up the equations that we were going to use was 2 and 3. So you're getting 10 marks for basically setting up the equations that you were going to use for your simultaneous equations. And then for equating them, we were getting 5 marks. And then for solving for our acceleration, we were getting 5 marks. So we had 25 marks for that first bit. An unusual year because then we were actually got not 5 but 10 marks. So it was a 35 mark question that year. Which doesn't happen too often because most of the time it's 20 and 30 or 25 and 25. So unless a question kind of contains a lot of workings, that's where you'd get more marks. Or if you go back to older years, sometimes you had a 50 mark question because there was no A or B part. It was just one whole question.